Okay, good evening, friends. So, myself, Dr. R.S. Chatterjee from Geosciences Department of IIRS. Today, we will be discussing on remote and techniques in geology and geomorphological studies. I think. So, today we will discuss on remote sensing and GIS techniques for geology and geomorphological studies. Okay. So, my outline of this lecture today, to begin with, that what are the applications in geology and geomorphology which can be potentially used by remote sensing and GIS techniques. Like you can see, there are many applications like geomorphological mapping. These are the basic areas of geosciences, rock types or lithological mapping, then geological structures, geostructural mapping, and many truly applications like mineral and hydrocarbon exploration, groundwater targeting, groundwater quality assessment, flow modeling, then construction material exploration, engineering geological investigation for many your engineering projects, environmental impact assessment, then geological hazards mapping and monitoring, and many more. So, but we should note one thing, that remote sensing is basically one tool, and this is a tool used from space. So this tool will be very effective and very powerful when it is used in synergy. Synergy with the complementary data sets like geophysical data, geochemical data, subsurface geological information, and ground truths. So there is no alternative to these ground truths and to these many other information like geophysical and geochemical and subsurface geological data. So we need as well, but remote sensing gives many first-hand information, and when we use remote sensing along with this, then this dimension of the study increases manifold. And now let us this mention about the outline of my lecture today. First, we'll discuss on the visual image interpretation or visual image analysis, followed by digital image enhancement. Very briefly, digital image enhancement and geological feature extraction, and followed by that, this is for optical images like aerial photographs and multispectral satellite images, panchromatic images, for basically for optical remote sensing areas. Followed by that, we'll briefly discuss on thermal remote sensing area for geological applications, and then microwave remote sensing, particularly radar remote sensing for geological applications. And after that, we'll be discussing on a little bit on the geomorphology and how remote sensing can help to identify geomorphological features, to map geomorphological features. Okay, and followed by we'll discuss very briefly about some of the salient applications in geosciences, which can be very efficiently done by remote sensing techniques. So to begin with, we are first we are going to start this visual image analysis or visual image interpretation, and basically a satellite image, or maybe if you talk about aerial photograph as well, but nowadays we are using satellite image mostly. Aerial photographs are very rarely we get. So a satellite image of the Earth's surface, it represents a stack of many thematic layers. What are those thematic layers? Broadly, it gives you the topographic information and the reflectance, what we get in the satellite image. So along with the topography, it also gives you the information about the vegetation. It gives you information about the land use, infrastructural information, gives you soil information, geomorphological information, lithology, and geological structure. So many layers are combined together in a single satellite image. Now, as a geologist, as a geomorphologist, it is the objective of the scientist to separate out the relevant information. So for us, for the geologist, from all this information, we need to separate geological information. That includes geomorphology, rock types or lithology, and geological structures. And how we separate this? For separating some of these features, some of the information we can extract directly by direct interpretation techniques, and many of the information we need to interpret by indirect, based on the indirect signatures. Okay, so now as we have been discussing that remote sensing and field-based information. So field-based information is very important. But what is the problem in field-based information and what are the problems in remote sensing? That should be very clear to us. First thing is remote sensing gives you a synoptic information, very regional view, bird's eye view. So you have an information, a very regional picture of the terrain we get. But in case of field-based information, we get the actual information about the geology at that particular point, but we get only macro scale information. So this is a difference between these two. So we need to use both. And this information, what we derive from remote sensing, that we can derive from direct signatures and by the indirect signature as well. That we will explain in the subsequent slides. So let us first see the interpretation elements. Those are direct interpretation elements from a satellite image. These interpretation elements, if we use, we can directly interpret some of the information, geological information from the satellite image. And there are many indirect interpretation elements as well. These are also known as terrain elements or geotechnical elements. Okay. So, interpretation elements, the objects of our interest are expressed in the image in terms of these are direct ones. So, these are tone or color or hue, then texture of the image, object, then shape or form of the object, then size of the object, then what is the pattern in the image, and the association of the object of interest with other objects in nearby areas. So these are these elements we need to study from a satellite image or aerial photographs. And geotechnical elements, those are indirect interpretation elements. These are landforms. So here the geomorphology plays a very vital role for interpreting geology of the area. Then drainage pattern, drainage alignment, many more that we will explain briefly. And vegetation pattern and alignment. Then land use pattern. Okay, so some of this information we can extract directly using these interpretation elements, and some of the information we cannot get directly. So for that we need to interpret it using the indirect interpretation elements, like landforms are the indirect interpretation elements. So information what we can derive from direct elements and information what we can derive from indirect these elements, that needs to be converged. So this convergence of information is very, very important in remote sensing data interpretation, remote sensing image interpretation. So convergence of interpretation from these direct elements, these are photo or image elements, and the terrain or geotechnical elements. This is basically the key for the successful visual interpretation of satellite image. Now, very briefly, we'll explain some of the slides on these direct interpretation elements, and we need to make a little hurry because we have a lot of slides to discuss. So the direct interpretation elements, this is the tone or hue. Here we have used the tone because it is a black and white aerial photograph. So what is tone? Tone is defined as the relative brightness of the object of interest with respect to the adjacent objects. Okay, so tone is defined as the relative brightness in a black and white image. Whereas if we use a color image or multispectral this pulse color composite, in this case color of the object in the image is very, very important. So this color is defined in the intensity hue saturation system. So color of the object will be important, but in this case we are mostly studying very elementary things, this tone of the object. Let us see here you can see the settlements, some of the area settlements, it shows very bright tone. It is a panchromatic information. Okay, so agriculture, these over clay rocks, like this is the areas, agriculture areas, you can see it gives you these medium gray tones. Whereas ultra basics, these are the ultra basic very dark areas. So ultra basic areas, it appears in a very dark gray tone. Some of the areas you can see like this here. So there may be some of the areas may be due to plantation as well. Now texture, it is defined as the frequency of tonal change, okay, over a particular length of the image, particular area of the image. So it is the result of the composite appearance presented by an aggregate of unit features. So the tone of the unit features, how these unit features are expressed over a length of the image. So what is the frequency of the tonal change? That is basically the texture. For example, this is an example, is a very typical example of your igneous, sedimentary and metamorphic rocks in the same area. So here both igneous, sedimentary and metamorphic rocks are exposed, and you can see the texture, those are very contrasting texture in different parts. For example, if you see the top area, here the tone is very, very smooth, whereas in the central area, the tone is very, very rough, very coarse. texture. Sorry. So here the texture is very smooth. Here the texture is very rough, coarse texture. Here you can see there are some striations. Here the striations. So here there are all the three kinds of rocks. This is basically sedimentary rocks. Those are very softer kind of rocks. So because of softer kind of rocks, it gives you very smooth texture. Whereas this is the igneous rocks, particularly this is granitic rocks. And you can see the very rough terrain. And this rough terrain gives you this very rough texture. And whereas it is a metamorphic rock, the metamorphic rock is characterized by your foliescence and schistosity. So it gives you a lot of striations along the foliescence and schistosity. So that you can very clearly interpret from here. Now we can use the shape or form. Shape or form of the object is very important. Like in case of geomorphic feature, like for example, if you talk about a point bar, it is a particular shape. If you talk about a oxbow lake, it is a particular shape. So the shape or the form of a particular object is very important. That based on that, like in a river or a stream, you can very easily identify from the image. Even a child can identify that because the shape, this meandering shape is very characteristic. So based on the shape, you can identify the features. Here, this example, what we have explained is the pattern. This pattern refers to the spatial arrangement of features. Now here you can see the banded pattern. Then banded pattern, and what kind of rocks are here? You see here, this is the bright. This bands, basically this is the limestone band. Whereas the dark bands, these are basically the marl. What is marl? It is the lime mud. So basically mud and along with this calcareous material. So here what happens in case of limestone, this is very hard and compact and there is no water is returning here. So vegetation does not grow. Whereas if you talk about the marl has lot of water and here it facilitated the growth of the vegetation. So this vegetation is a panchromatic, this your picture. So that is why the vegetation appears in the dark tone, whereas this limestone, which is very hard and compact and there is no vegetation, it appears as a bright tone. And you know limestone has this very high reflectivity. So this banded pattern is basically this the alternate arrangement of the limestone and marl. And here if you see the geological structures, very interesting geological structure you can see the folds, you can see the faults, you can see the joints, you can see the fractures. So basically if you see this feature, this is a fault. Here you can see the displacement or offset of the features. Whereas you can see many features here, there is a regular arrangement of the systematic arrangement of the discontinuity planes. Those we call the joints. So basically if there is a random pattern, these we call fractures, and when the fractures are regularly arranged, then we call it joints. Basically there are the both are the planes of discontinuity. One is arranged very randomly, another is arranged systematically. Okay, and fault is a fracture with the offset of the features on either side. So that we can very easily identify from the satellite image here. Now we see association. What is association means? Association means this, you are interested to identify a particular object. Okay, so this particular object is associated with some neighboring object. So now for identification or for recognizing this object of your interest, how the associated features, how the neighboring objects helps you to interpret. That is what association helps us. Like for example, if I ask you what this gray tone, these threads represent, what the material is, it may be a little difficult for us. But if you see in the next slide, it will be very easy. Because now we can see these are the volcanic cones. This is a volcanic cone, this is a volcanic cone here. Now we can understand the material surrounding these volcanic cones, these are the pyroclastics. And these are the threads, these light gray or medium gray threads, these are basically the lava flows. So it is very easy for us to interpret, but what is basically helping us, it is the association of these features. So these features associated with these very characteristic features. So based on this association, we can interpret the rock types, the features very easily. Now, so these are this compilation of all the direct interpretation elements. So this is the tone or hue. Basically, tone means the relative brightness. Texture, this is the frequency of tonal change. Then shape or form. Then pattern, the spatial arrangement of features and association. So these are the things important for direct interpretation of the features from satellite image or aerial photos. Now, these indirect interpretation elements, these are also known as terrain elements or geotechnical elements. These are broadly classified into landforms. So landforms we'll explain more elaborately later on in geomorphological discussion. So landforms is landforms and landform association that resulted from the geology of the terrain, that is the rock types, then attitude of the rock formation, geological structure, then this rainfall, then metamorphic processes. So many things are important for the origin of the landforms and their characteristic shape of the landform. So this landform is very, very important for interpreting the objects or interpreting the geology of this area or the geomorphic geological processes over this area. Then followed by drainage. So here drainage, there are many these elements of the drainage, like what is the shape of the channel, channel form, drainage pattern, then drainage texture, drainage anomaly, and there are some indices, drainage basin indices or morphometric indices. Many more things are there in the drainage, these elements, which help us to interpret the geology of that area. Okay, and very briefly, there are vegetation and land use element is also very important for indirectly interpreting the geology of the area. For example, vegetation density, vegetation cover. So where the vegetation density is high, that means here the underneath material it brings the growth of the vegetation. Whereas the nearby area, if the vegetation density is very less or there is no vegetation, that means here the material is not favoring. That means there may not be any soil at all. Okay, so then vegetation pattern, then alignment. Let us say that the vegetation is aligned in a particular line. So then we can say there may be a fracture along which their soil has been formed, what is available for the growth of the vegetation. So that is why you are getting some alignment of the vegetation. So the vegetation and as well as land use as well. Land use, it basically represents the topographic information about this area, what is the slope, whether soil formation is taking place in this area or not, what is the thickness of soil, what is the nature of soil, whether the soil available here, it is supporting the agricultural or agriculture or not. Okay, so these kind of information you can indirectly infer from that. So what are the rock types, whether the rock types is stable enough for foundation for the settlements. So all this information you can get indirectly from the land use and from the your vegetation cover and vegetation density and their pattern and orientation and alignment. So these things we can do, like here the land, talk about the landform. See here the landform is the alternate ridge, this is the ridge, there are valleys, again ridge, then valleys, like this. So ridge valley topography we can see here. We'll explain here later on. What does it mean? It is basically there is a layered appearance of the rocks. So and these rocks, some rocks are developing the ridge and some rocks are developing the valleys. So what does it mean? The rock which is developing valley, that means this rock is a soft rock, that is why it is eroding very faster. And whereas the rocks which is developing the ridge, that means these are hard and compact rocks. So if in a sedimentary terrain it may be sandstone, this hard and compact rock may be sandstone, as the soft rock may be shale. So like this you can indirectly interpret here the attitude of the beds, they are parallelly aligned. So they are sandstone, they are shale, and they are aligned parallelly. And one is this hard rock, another is a softer rock relatively. So those things you can interpret, but all this interpretation you are doing, it is indirectly. Now like here, if it is a drainage, this drainage pattern looks like this tree. The branches of the trees you can see, but it is basically drainage. It is the main drainage. This is streams are flowing down and like this. So this kind of dendritic, this drainage pattern is known as a dendritic drainage pattern, where it will develop. This kind of drainage pattern develops where there is no geological structural control, where the rocks are homogeneous or flat-lying rocks, like this. So we'll explain more. And here, for example, you can see there is a trellis drainage pattern. So there the main drainage are, whereas the sub-drainage, these are the drainage across. These are shorter drainage. So this kind of drainage where it will develop, where there is the alternate ridge and valley kind of topography is available. So here this kind of drainage can be developed. So here what I had been discussing in the previous slide, that is more elaborately it is given, like dendritic drainage, what kind of geological interpretation we can do. If we find the dendritic drainage, like interpret that this is the horizontal sediments or uniformly resistant crystalline rocks like granite, okay, and regional slope at this moment is gentle. So here the regional slope is gentle, or at the time of formation of the drainage it was gentle or flat. So this is what is the interpretation of dendritic drainage. Then parallel drainage as well, how to interpret where the parallel drainage develops, where the slope is moderate to steep. Trellis drainage, as I already told, dipping or folded sedimentary beds, those are parallelly arranged. So in this kind of terrain you will get this trellis drainage pattern, main drainage parallel to each other and has this soft drainage, the shorter streams are across it. These are shorter in size and they are perpendicular to the main streams. And rectangular drainage is this. If you see the drainage, the stream develops a rectangle sort of this shape or form. So here the streams lacks regional continuity and controlled by orthogonal fracture systems. So what kind of interpretation you can do? You can say here, if you find a rectangular drainage pattern, you can say here the fractures are orthogonal. Orthogonal fracture system is there. Okay. Then radial drainage like this. If you find this kind of drainage from the satellite image, then we can say then there is a dome, or this dome may be a structural dome. The dome may be an intrusive dome. So any kind of dome is there. And if you get this kind of drainage, this is known as annular drainage, where this is incomplete this circle followed by radial drainage. So this is known as annular drainage. These are definitively, it indicates that possibly these are structural domes, but in some cases it can be intrusive, igneous intrusives as well. Now drainage density and significance, if we talk about that, so drainage density is very, very important. So drainage density is basically controlled by some of the factors. What are those? These factors are these: what is the resistance of the rock formation? If harder rock, then drainage density will be low. If the rocks is softer, then drainage density will be high. But what is drainage density? Drainage density is defined as the total length of drainage in a unit area. So it is the total length of the drainage in the total area divided by area itself. So this is the drainage density. So where the drainage density is more, like in this area, drainage density is more. Whereas here the drainage density is relatively less, and here also drainage density is relatively less. So drainage density will be high where the rocks are softer, and drainage density will be low where the rocks are harder. And permeability of the rocks, where the rocks are rocks, then drainage density will be low. Where the rocks are impervious rocks, then drainage density will be high. Again, depending on the topographic slope, if the gentle slope, if the slope is gentle, then drainage density will be low. If the slope is steep, because your cutting power of the drainage is more, in this case, in steep slope, drainage density will be high. But again, everything is controlled by the rainfall and the climate of this area. So now here the drainage density, drainage map you can see. Based on that, can you make any kind of geological interpretation based on the drainage density parameter? So that you can. Let us see in the next slide. So you see here. So here you see this, all these along this belt, drainage density is very high. So in this area, the rocks is possibly impervious. So if it is sedimentary terrain, this rocks is possibly representing shale. Whereas if you talk about this area, here the drainage density is less. Here this rock is possibly sandstone. So here both you can identify, you can interpret the these formation trends. So this outline of your rocks, and as well as basically geological structure as well as rock types, both you can interpret from this. So in visual image analysis, that what we are winding up is basically, if given a satellite image or aerial photograph, you have unknown categories of objects you need to interpret. So some of the features you can interpret spontaneously, that is based on your memory database. For example, if I give a satellite image with a river in it, even a child can tell that this is a river. So a memory database, from the memory database, one can interpret some of the features. Okay, then followed by then logical inferences, that is the using the direct and indirect interpretation elements as I discussed now. So this is the your photo or image elements as well as geotechnical and terrain elements. So using those logical inferences, you can identify some of the objects, followed by this ground truthing and local knowledge from the existing maps. Then you can visit this area and you can collect ground truth. Based on that, then you compare what you have you are interpreting and what actually it is there in the existing maps or in the ground truth. So then finally you make the known classes from the satellite image for the entire area. For example, ground truth you will not be doing for the entire area, you will be doing selectively only for some points. And this truth you use for selective points, you can extrapolate for the entire area, and you can have this geological information for the entire area of this your image. Now, how to interpret different rock types? Like we have broadly three kinds of rocks, like igneous rocks, sedimentary rocks, and metamorphic rocks. If you talk about the igneous rocks, so igneous rocks, these characteristics of the igneous rocks like this: homogeneous, they are massive, they are resistant, they are hard, they lack bedding in general. But in case of extrusive rocks, you can have some bedding or layering. And characteristic landforms are the volcanic cones, dikes, inselbergs, plateau, mesa, butte. characteristic joint patterns are generally radial, columnar, and sometimes orthogonal as well. But in case of sedimentary rocks, these are softer rocks. First thing is they are softer rocks, and their dissection is many more here. And there is a presence of bedding, so layered structure is very, very important. And there is a differential resistance because there is a layered structure or bedding structure is there. Differential resistance of harder rocks, that harder rocks can appear as a ridge, whereas the softer rocks can appear as valley. So if you have a sandstone shell alternating sequence in an area, so the sandstone will finally sandstone will develop a ridge, whereas the shell will develop a valley. So you will finally get a ridge valley topography. And characteristic landforms are the like mesa and butte in case of horizontally stratified rocks, whereas hogback, cuesta in case of homoclinally dipping strata. In case of metamorphic rocks here, what is very, very characteristic for interpreting metamorphic rock is this presence of regional foliation and schistosity in metamorphic rocks. This regional foliation and schistosity that undergoes this differential weathering along these planes, so that gives you striated appearance in the satellite image. So based on this striated appearance and some deformation structures, that you can interpret metamorphic rocks very nicely. Metamorphic rocks are more resistant than short sedimentary rocks. It lacks bedding, and as I already told you, the deformation structure helps us to understand that this is a deformation terrain. It's a metamorphic terrain. Okay, so based on that, you can interpret this. Perhaps this is a metamorphic rock. For example, this is a sedimentary terrain. Here the alternating sandstone and shell, and you can see there are ridge valley topography that I have already explained to you previously. And here you see, here this is again a sedimentary terrain because there is a layered structure is very, very clear. Dissection is very, very high. In this case, drainage density is very high. In this case, drainage density is little less. What we can say that here the underneath rocks, this underneath the alluvium, it is basically alluvium. You can see you are seeing at the surface, but underneath the alluvium, the rocks are perhaps their shell. Because this is shell, so this is impervious, so there are a lot of drainage density is very, very high. But in this case, in some areas you can see the exposed rocks, but in many of the areas this is alluvium. So underneath the alluvium, the rocks are perhaps here the sandstone. Why I am interpreting like this? Because in this case drainage is very, very less compared to this area. So sandstone is more permeable. As it is more permeable, so it allows percolation of water, or surface water underneath. So it does not develop drainage very frequently. So drainage is less in this case. Okay, so you can see here there are some displacement also. So from this, based on this offset of the beds, this is this trend of the beds, isn't it? We can call it the strike of the beds. Okay, here you can see there is an offset, there is a displacement. So there you can identify fault here, there is a fault here, there is a fault here. Even you can measure the displacement based on the, if you have the scale of this your photograph. Now, if you see here, this is a igneous terrain, basically volcanic terrain. This is a volcanic cone. This is the plateau, volcanic plateau. And very interestingly, you can see here, these are basically the dikes. Okay, because dikes are made of igneous rocks, these crystalline rocks. These are comparatively harder than the background to this sedimentary terrain. So it appears as the wall rock and is exposed surrounding the host rock or these softer sedimentary rocks. So very easily you can interpret the dikes here. And here you see this is basically it is a metamorphic terrain, granitic gneissic terrain, and here you can see these your foliations, so gives you the striations, and these foliations also you see this is the trends of the foliations. It also shows some kinds of displacement here with respect to this your fracture planes. So these are basically some kind of displacement also you can observe here. Now this is, you can see again this metamorphic terrain can be very easily identified because based on the striations, which is basically this is from your regional foliations or this schistosity planes. It gives you the striations and also this folded structure. This is basically a deformational structure. So folded structure. So from all these evidences, you can very easily interpret that this is a metamorphic rocks. Now we are coming to the geological structural interpretation. So we discussed about the basic interpretation elements, these direct interpretation elements, indirect interpretation elements, followed by how to interpret the different rock types, broadly igneous, metamorphic and sedimentary rocks. Now how different geological structures. So broadly geological structures, we will be discussing about the folds, faults, lineaments. So faults may be exposed faults, maybe buried folds. In case of exposed folds, now you have to see whether there is a change in strike of the beds or there is a change in the dip of the beds. That is the definition of a folded structure, isn't it? So recognizing a fold, you need to see whether there is a curvature of the strike of the bed and if there is a change in the dip of the bed. So here you can see this is the strike of the beds, and you can see the nicely how the curvature has been formed by this this folded bed. So this is a folded structure. But what is the geometry of the fold? If you want to understand, if you want to decipher that, for that you have to have the what is the dip of the folded bed at different points. What is the plunge of the folded bed? You may not get exactly what is the how much is degrees is the dipping, how much degrees it is plunging, but you can get very qualitatively how much is the dip of the beds here, here, here. So what is the basis for that? It is based on the flat irons. The irons what we use for pressing our clothes. So these irons, you can see the triangular facet like forms, isn't it? So like if you see a broad iron like this, okay. So here this iron is pointing upward. So here this criteria is that flat irons is pointing opposite to the deep direction. So either it's a larger flat iron or is a smaller flat iron. See it carefully that these are pointing upward. So that means the beds are dipping towards this. And also there is another criteria on flat iron is that size of the flat iron or width of the flat iron is a function of the amount of the dip. If the size of the flat iron is large, that means the width is large, then this bed is dipping gently. Okay. In this case, you see here the flat irons are larger. Here also larger. Here is also larger. But if you see here, the flat irons becomes very narrow. So what does it mean? Here the beds are dipping gently, whereas here the beds are dipping very steeply. So from this gentle dipping folded bed and how this dip of the folded bed is changing to steeper one, so you can interpret the geometry of the folded bed. Now here you see that here also how do you interpret a folded structure? See the flat irons are here, here, here. So from this flat iron we can interpret very easily that it is the beds are dipping towards this direction. Similarly here also beds are dipping towards this direction. So if the beds are dipping towards each other, what does it mean? Basically means that it is an antiformal structure, isn't it? This is a satellite image from the northeast. You can see the rock formations like Tipom, then Bokabil, then there is Bhuban. Okay, so all kinds of rocks are there. So Tipom is alternating here, symmetrically repeated. Here is Tipom, here is again Tipom. Isn't it? Bokabil is here, here is Bokabil. So based on that symmetrical repetition of the beds and dip of the beds towards each other, that tells us that it is a antiformal folded structure. Now from the drainage also you can interpret folded structure, but it is not a very confirmatory this criteria. So generally radial or concentric drainage are there generally associated with anticlinal and synclinal. Here the drainage is you can see it is a radial. So radial drainage it says that there may be an anticlinal structure, and if the drainage is concentric, that represent that it may be a synclinal structure. Now if the folds are buried, so there is it is not cannot be seen from the satellite directly because the fold is buried. Then how we can interpret if there is a fold or not? Then sometimes what we can use, the compressed meanders, some of the drainage anomalies we use to interpret a fold. Like compressed meanders here, you can see the compressed meanders, okay, and there is a folded structure. After this this stream crosses this folded structure, it becomes then normal. The course of the stream becomes normal, okay, so and resumes its normal course, isn't it? So this is from the drainage anomaly. You can interpret the buried fold. Here, if you find the double drainage deflection, so there may be an structure or there may be a folded structure in between these two streams. So indirectly you can interpret there may be a buried fold. But this is very interesting. If you find the parallel drainage deflections, okay, so this basically indicate that it is cutting a folded structure, okay. So if this parallel drainage is very much visible when there are the parallel faults or parallel lineaments are available, parallel fractures, parallel drainage can follow parallel fractures or parallel lineament or parallel faults. But when there is a deflection, this parallel drainage deflection, so basically it represents that perhaps there is a plunging nose of a fold, it is cutting, that is why it becomes the acute angle with respect to the fold, so that it can get more cutting force to cut the drainage, and after that it becomes again, it flares up. Now here if the satellite image of this area if you interpret, see what kind of structure you can interpret, very major structures. Here see the drainage becomes rectilinear for this segment, and also you can see this land use, land cover of this area. You can see some kind of anomalous pattern here, and this is this vegetation shows a dense vegetation along this trend. That means that there is a rock types. This is underneath the rock types formation is like this. Okay, it shows curvature of the rock types. So what does it mean? It means that there is a fault here. So we can very easily interpret a fault here. Okay, so although this is in a remote sensing terms we call it a fault, basically it is a ductile shear because there is no detachment of the bed has taken place in this case. Now this image, if you see, you can see that there are faults, there are fractures, okay, and there are some on this systematic pattern, systematic arrangement of the fractures. So these are basically joints. So you can see joints, you can see faults, you can see fractures. So that you can interpret very easily from the satellite image. Okay, sometimes this your some kind of geomorphic anomalies. Geomorphic anomalies help us to identify faults or faulting. Like in this case, this parallel alignment of the sag faults. Okay, parallel alignments of the sag faults. It indicates there is a strike slip fault. Okay, how this parallel alignment of the sag faults develops? This is the mechanism. So when there is a strike slip faulting taking place, there are some restraining bands and there is some releasing bands and there are some restraining bands. In the restraining bands, because it is the direction of displacement in that acute angle, so there is this here is this band getting strained, and what will happen? There will be a mound or a will be developed. Whereas when there is a releasing one, then there will be fracture, will be opened up, will be this open space will be developed that will make a pond, or this pond when filled up with water. So this is develops a pond, and this systematic, this alignment of the ponds along a line that indicates that there is a strike slip fault. Okay. Now this, if we are talking about this is about the visual interpretation. Now, if what kind of satellite image is required and what kind of satellite image enhancement will be required for this your geological interpretation, particularly for geological structures. Like here you see this, we have given two images of the same area. One image during summer time, another image during winter time. See here, in case of summer image, these geological structures are not very clear, very subdued here. But if we use the winter image, geological structures are very much highlighted. So we should use winter image because in this case the sun elevation is small, so it gives shadow effect is highlighted here. And most of the geological structures, many of them are expressed through this your topographic your elevation change. Now, what kind of image enhancement we should adopt? Mostly for geological structural these features identification, we generally go for this spatial filtering and this transformation, like principal component transformation. So in this case, this is the original satellite image. It is a band 4 TM image. So if you can identify the geological structures like we can identify here like this, in that case you apply some gradient filter or directional filter across this trend of the geological structures. But in some cases, if you don't identify any geological structures or trend of the geological structures very clearly, then first what we do, we first apply the non-directional or Laplacian filter. So Laplacian filter is irrespective of the direction. So it highlights in all the directions. So in this case, we will be able to identify some of the geological structures if available in this area. And after we identify the geological structures which is not very much highlighted so far, then you can apply the directional filter across these geological structures. So this is what kind of techniques you can adopt for this thing. Now we are coming to thermal remote sensing. So in case of thermal remote sensing, this electromagnetic this wavelength region here, in case of optics, they have used the visible, near infrared and short wave infrared. So here the range in case of optical remote sensing is 0.4 to 3 micrometer. Basically visible is 0.4 to 0.7 micrometer, followed by near infrared and then short wave infrared. Now in case of thermal, the electromagnetic region is 3 micrometer to 35 micrometer. So this region is popularly known as the thermal infrared region in terrestrial remote sensing. But in this total region, we use mostly the 8 to 14 micrometer region. Why 8 to 14 is so much useful? Because the ambient terrestrial temperature, the normal earth temperature is around 9.7 micrometer. Okay, so the peak of the earth's blackbody radiation occurs at around 9.7. So 9.7 comes in this range. So if you are in this range, then what will happen? You can get the maximum radiation from the earth's surface. If the radiation is maximum, the signal will be high and the noise will be less. So you can very easily interpret the signal over the background. Okay, so this in case of 8 to 14, there is another advantage for 8 to 14 region. This excellent atmospheric window lies between 8 to 14. But this atmospheric window, that means the transmit energy thermal region is a little less. This also exists in 3 to 5 and 17 to 25 micrometer, but because of 8 to 14, this transmit energy is maximum. And moreover, interpretation in the 3 to 5 micrometer region is a little complicated. Why? Because in this region, if you use daytime image, during daytime image, there is some solar reflection component also will be included with the thermal radiation component. So that is why this 3 to 5 is a little difficult to interpret, and 17 to 25 is still not well investigated. Why? Because in this region only the cryospheric applications, so where the objects are very low temperature objects, can give you some good amount of radiation. Otherwise, this radiation will be very, very less in this region. So prominent and diagnostic narrow spectral features, okay, that occur in this again. So silicates, mostly these different kind of rocks. So silicate is the major chunk of that. If you see, so prominent and diagnostic, these spectral features are occurring. That is silicate, these absorption features is known as crystalline bands, that occurs in this region around 10 to 12 micrometer. So that is the reason why 8 to 14 micrometer is most important for our this geological application. Now this is your, you can see this is the your thermal region 8 to 14. This is 3 to 5 and 8 to 14, and then followed by this this other one. Okay. Now this is the thermal spectra. If you see the thermal spectra of geological materials, okay, there are the thermal absorption peaks are very characteristic for different rocks. So using these absorption peaks, you can identify different rocks. But at this moment, thermal images, what is available from the satellite data, thermal images, the resolution is a problem. So we don't have very finer resolution thermal data. Here you can see the behavior of the crystalline band. That is very, very important for the your silicate rocks. You see here where the silicates this is the rocks are low in silica content. Here the absorption this peak is towards 12 micrometer, whereas if the silica content is high, like granitic rocks, okay, so in this case this absorption peak is towards the shorter wavelength. This is closer to 10 micrometer. But when it is a ultra basic rocks like your or the basic rocks like gabbro, then it is towards 12 micrometer. So this phenomena also very much important for interpreting the different kind of silicate rock. And this is the standard these values of your capacity, thermal diffusivity, thermal inertia, the different kind of physical parameters which can be used for interpreting thermal images. So most important parameter is thermal inertia. So thermal inertia image can be used for this interpreting the geological materials. So this is the last slide in thermal remote sensing. So you can see here this is Landsat TM FCC 754. It shows the broad lithological categories like dark volcanics. Okay, these are the dark volcanics. Then they are altered products. Okay, and there are limestones, like this is the bright areas. These are limestones because reflectivity is very, very high. But in thermal image, if you see what happens, the volcanics gives you the brighter signature, isn't it? Because it absorbs a lot of solar radiation. Whereas altered zones, it appears this is the altered zones, it appears in dark tones. Why? Because here the solar radiation absorption is much less. Whereas in case of limestone, it is appearing in between. This is moderately light tone. Okay, so sometimes it is difficult to distinguish from the volcanics as well. Now we are coming to the microwave remote sensing, particularly radar remote sensing. So this is the microwave remote sensing family. Okay, very briefly. So microwave remote sensing can have a passive microwave remote sensing that sends the radiation from the Earth's surface in the microwave region. So this is the passive microwave remote sensing, and this is the active one. In this case, what happens from the satellite or from the aircraft or from the spacecraft, this is your pulse in the microwave region is transmitted, and this the microwave radiation, it is interacted with the Earth's surface materials, and after the interaction, it comes back and from the this return signal which is received by the antenna. So based on that we can interpret different materials or different kind of features and different kind of information we interpret. Like in case of active, this is also known as your radar remote sensing, so radio detection and ranging. So it can be imaging radar, it can be non-imaging radar. In case of imaging radar, it again there are classes are there like real aperture radar or RAR or side-looking airborne radar, and then presently what we are using mostly is a synthetic aperture radar because here the resolution is good enough for our standard applications. And this is the non-imaging radar, this is altimeter and scatterometer. Now if you see this radar remote sensing, what are the uniqueness, what are the advantages of radar remote sensing beyond this optical remote sensing? Like it can operate both daytime and night time because it is active one. So because it is active one, you can have information during night time. So in night time information also you can have. And similarly, it can be used in the polar regions because in polar regions remain dark for major part of the year. So during that time when the polar region remains dark, you can use radar remote sensing for getting information about the polar regions. It also penetrates through cloud. Okay, so it penetrates through cloud. So there is cloud is not a problem. Smoke is not a problem. Like here volcano, smoke you cannot see anything if you use the optical remote sensing. But if you use the radar remote sensing, you can see very clearly. Like here, if you see the optical remote sensing Landsat TM data, because of cloud cover, you cannot see anything. But if you use radar image, you can see very clearly. It's again there are other advantages like it penetrates through vegetation. So when it penetrates through vegetation, you can have information about the terrain. Like in this example, we have used X band and L band. X band is a shorter wavelength, 3 centimeter wavelength, whereas L band has a wavelength of around 23 centimeter. So in this case, what happens here? The metal rod covered by vegetation is not visible in case of X band, but when you are using L band, it penetrates through vegetation, so you can detect the metal rod underneath. Like in this case, bring example here. See band 7, which is a wavelength of 10 centimeters, band P, wavelength around 60 to 70 centimeter. See here, there is no feature is detectable here, but here you can see there are the features. This is you can detect this basically underground pipeline. You can detect here. Okay. So subsurface information you can have. Like in case of geology, paleo channel, buried channel, you can interpret from this. Now, how radar remote sensing is important for geology and geomorphology. Why? Because there are 3 criteria why radar remote sensing is important. Because it is very sensitive to surface geometry, surface slope. So it's sensitive to surface geometry or surface slope. So it provides information on geomorphology and geological structure. Because geomorphology is nothing but it is the information about this topographic variation of the different elements. So it is even little more than that. And geological structures, many of the geological structures are expressed to topographic variation. So based on this sensitivity to surface geometry, so geological structure and geomorphology can be interpreted very nicely, much better than the optical image. And its sensitivity to surface roughness, it helps for interpreting some of the rocks, some of the rock types, particularly in case of vegetated terrain. Okay, but optical remote sensing has much more potential for interpreting the different rock types. But if you talk about the geological structure and geomorphology, radar remote sensing is much better than optical remote sensing because it can highlight the topographic effect very much. And this radar remote sensing, it has a very sensitive to moisture content, or dielectric property of the materials. So it is useful for unconsolidated material or soils. So for differentiating the unconsolidated materials from compact and hard rocks, you can very nicely use radar image, radar remote sensing image. So these are some of the uniqueness. So you see here, this is one of the sample image I am using, RadarSat 2. You can see this is the broad bright area. So and this is your medium tone, whereas this area is a darker tone. So basically here are 3 rock types. Where the limestone is a very rough, so this is limestone appears bright, and this is the sandstone, which is relatively less rough, and this is the shale is very smooth. So because surface roughness is very important for radar remote sensing. Surface more rough means more scattering, and if it is more scattering, then there will be more back scattering to the antenna because it is active remote sensing. So in case of limestone appears a bright tone, whereas sandstone is less rough, so it is appear medium tone, whereas shale appears darker tone because surface is getting more and more smooth. Now if you see the geological structure, you see one optical image we have used here for the same area and one radar image. See, in optical image, geological structure is not very clear, but if you use the radar image, geological structures are very clear here. Here we have merged optical image with radar image. Now you see, after merging radar image with optical image, then what is the beauty of this hybrid image or merged image? You see here, in this case, the lithological discrimination is better because you are getting the spectral information from the optical data. Geomorphology is better because you have lot of radar information, this topographic information from the radar data. Like in this case, you can see the hills are very much highlighted. You can see the buried channels here is very much highlighted here. You can see this is a crater boundary, is very, very short. You can see some of these aeolian features like longitudinal dunes. These are very much clear, which is otherwise not clear in optical image. Because we have merged radar image with optical image, we can have both information from the radar as well as information from the optical data. Optical data gives mostly the spectral information, whereas radar data gives mostly the surface roughness and surface roughness information and this shallow subsurface information, because radar this your signal can penetrate the earth materials depending on the wavelength again. So if the wavelength is longer, it can penetrate more. If the wavelength is shorter, then it can penetrate less. So we can have some subsurface information, we have topographic information, we have spectral information. All these together, our interpretation is much better than using optical image alone. Now, okay, so we'll discuss a little bit on the geomorphology. So after this geomorphology, maybe we'll take a little break of 10 minutes, and during the time we can discuss about the questions. You may have many questions with you, but for 10 minutes we will discuss about the questions what you have, and after that again we will start the lecture after 10 minutes break. So now to continue some more slides, that is on geomorphology, the fundamental geomorphic elements here. These fundamental geomorphic elements is based on the height information. If we do that, there's an upland or highland, rather highland, plain and valley. So highland consists of hill and plateau. In case of hill, there is the height, this is varying from one point to another, whereas in case of plateau, this is a flat topped hill. Plateau can be dissected plateau, it can be non-dissected plateau, whereas hill can be structural hill, it can be denudational hill, and plain can be alluvial plain, coastal plain, aeolian plain, depending on the process which is responsible for the formation of the or development of this particular plain. Valley may be intermountain valley, strike valley, synformal valley. This in geomorphological study, landforms is very important, and it basically it is the unit of geomorphological study. So what is a landform? Landform are certain terrain features formed from by natural processes which have a definite composition and range of physical and visual characteristics. Okay, landform is characterized by its unique topography. So topography is very important for a landform. It has an unique topography and composition and structure. And finally, landforms are multivariate features. So development of a landform is responsible by many factors. What are those factors? Lithology, what is the rocks in this area, what is the geological structures or attitude of the beds, what are the geomorphic processes operating over this area, and what is the climate prevailing in this area, and how much time. So these are the factors all together, they develop a landform. So a particular landform tells about these many information exists there, what is the geomorphic process operating, and about the climate and time. Now this, in case of this thing, recognition, and in geomorphological study, what is important is the recognition of the geomorphic processes and materials. So here the what are the contents of the geomorphic map is very important for understanding geomorphological these studies. For in the contents of geomorphic maps are very important, because a geomorphic map consists of many things. What does it basically represent? In a geomorphic map, there is the morphography, there is a morphometry, there is a morphogenesis, there is a morphochronology, and there is a morphodynamics. Morphography basically geomorphological representation of landforms and their extent of occurrence. So basically depends on the shape and form of the landforms. Morphometry is the actual measurements. What is the size of the landforms? What is the slope? What is the terrain of the landforms? Morphogenesis, what is the process? What is the origin of the landforms? What is the mechanism for the development of the landforms? And morphochronology, there are a number of landforms exist in this particular area. What is the chronological arrangement, time sequence? What is the chronological arrangement of the landforms, time sequence, and distinction between the different landforms at different ages? And finally, morphodynamics. What is the dynamics of the landform, particularly the active landforming processes? So all those things together we need to understand. Then only the contents of the geomorphic maps will be clear to us. So then only we can prepare this nice geomorphic maps if we understand what should be the contents of a geomorphic map or geomorphologic map. Okay, so this geomorphic can be interpreted in terms of the geomorphic processes. So geomorphic process may be exogenetic, that is where the driving force that is coming from the external sources, that is from the force of gravity. So the exogenetic processes like fluvial, aeolian, glacial, coastal, and the slow processes. These are giving different kind of geomorphic terrain, different kind of landforms, and endogenetic processes like those processes where the driving force coming from within the earth. So this is endogenetic. So genesis from inside. So the driving force for the formation of these landforms coming from inside the earth. So basically it represents the folding and faulting. So structural or tectonic landforms, these folding, faulting, different kind of things. And another is volcanic landforms. So one is the structural or tectonic landforms due to the folding, faulting, and different kind of tectonics. Another is due to volcanic processes the landforms developed. And this is one slide I want to show you. This is very interesting. This is a Kosi fan you can see in a panchromatic image, whereas this is your Ghaggar river. This fan that is basically Panchkula area. So multiple satellite image. This is the alluvial fan of the Ghaggar river. This is the Panchkula area. But you can see even this area has been so much modified by these land use practices. All are settlements now. All have been modified. The entire fan has been modified by the settlements. But even then, from the satellite image, we can very clearly identify this fan. And in this case, you can see the migration of the streams. Initially, the stream was somewhere here. Then the stream has migrated here. Then it is here. Here it is here. Again, it has migrated now. So this is what is happening for the Kosi river. Now you can see these fluvial geomorphic landforms, Like if you see, this is in this case, this is an example from near Barak River in the northeast. So you can see this is the oxbow lakes. So clearly we can identify the oxbow lakes. This is the natural levees. Okay, there are the sandbars. Okay, so these geomorphic landforms very clearly we can interpret from here. These are the structural hills. Here we can interpret, isn't it? So now it is the extended view of this area. You can see the oxbow lakes, the alluvial plain. These are these natural levees. Some are current natural levees. Some are these old natural levees, these new natural levees. So those things we can interpret very nicely from the satellite image. Now here there are 4 images are given. In this case, this is the area where you can see. I suppose you can see well. There are the different river terraces are available. It is not very clear, I believe. Okay, so here you can see this drainage shows some kind of anomaly here, but here you can see this thing, your natural levees boundary. These some of your sandbars and alluvial plains, and here you can see this is some of the streams. This represents the abandoned channels. These are abandoned channels, but if the discharge increases, these channels can maybe again be functional. Okay, here this meander scroll. This scroll, like it is moving like this, it appears, and here you can see this paleo channel belt here. Okay, so paleo channel belt you can see. So this kind of interpretation you can do from the satellite image. Now, if you see this slide, it is a coastal geomorphology. So this is a Bay of Bengal. So here you can see very nicely the estuary area. You can very nicely interpret the creeks. You can very nicely interpret the mangrove swamps area. Is the mangrove and mangrove swamps and mangrove the mud flats. Okay, here there is the beach area. You can interpret some of the mud flats, even mangrove with mud flats. You can interpret. Okay, so this area is basically purely coastal landforms, and up to this estuary bottleneck, this area can be interpreted as this coastal alluvial plain, and beyond this estuary this neck. Above this is only alluvial plain. So if you interpret the geomorphology, you can see like this. So this is the alluvial plain, this is the coastal alluvial plain, and this is the coastal plain. Basically, this is the mangrove swamps and mangrove mud flats. So some of the applications we will discuss. One of the major application is groundwater targeting, groundwater budgeting, this recharge estimation, identification of the groundwater recharge, artificial groundwater recharge sites, groundwater flow modeling, groundwater quality assessment, and groundwater pollution. So there are many applications. So here, for example, we have shown groundwater potential map of one of the topographic sheets, 1 is 50 scale topographic sheets of national capital region. This we have prepared in a project of the national capital region, this groundwater potential and quality of national capital region we have done. And this is a large scale information about the Delhi region. This both here we have combined groundwater potential and groundwater quality. So here different shades represent groundwater potential, whether it's a good potential or bad potential, but within a particular class with a particular potential, what is the quality of the water? That we have combined this quality information with the groundwater potential information. How much qualitatively groundwater is available? Is groundwater available is very high, or groundwater available is very low? And if groundwater available is high or low, what is the quality of groundwater? Whether quality is good or quality of bad. If the shade is a lighter shade, then quality is good. But if the shade is a darker shade, then quality is bad. So it is a combination of both information. Based on that, one can make a decision that in this particular area, groundwater is available in a large quantity, and the quality of the groundwater is good, and or let us say in a particular area groundwater available is a large quantity but quality is not good. So that area is not very useful for this your consumption. Now in this case, you can see the groundwater flow. The studies has been done. So how groundwater underneath the groundwater means what? It is the water underneath the earth's surface. Isn't it? So how the groundwater flows underneath the earth's surface? So that follows the hydraulic gradient, isn't it? So water table or hydraulic gradient, piezometric surface. So it was this water table or piezometric surface, the hydraulic of the groundwater. Okay, so here we have made an attempt to understand what is the groundwater, how the groundwater flows in this particular area of Dehradun. Now, this one of the very important applications of remote sensing and GIS is in mineral exploration. So this can be used for mineral exploration, for petroleum exploration. Okay, and like for example, in this case, this is an example of base metal exploration in this Rajasthan area. Similarly, there is mineral resource information system, GIS based information system. So here we have put all the information about the mineral deposits, like what is the nature of the mineral deposits, what is the mode of occurrence, what is the this nature of the reserve, what is the proven reserve, or this is predicted one. Okay, and this reserve characteristics. So this kind of information you can have from this kind of information system. But this information system you can, this is a framework, but this kind of information system can be this upgraded and upgraded with more and more information. Then you have a very exhaustive information system. This is an mineral exploration, particularly those are surfacial minerals. Here the spectral information of the minerals are very important. And here there is hyperspectral remote sensing, which is one of the emerging area in remote sensing. Hyperspectral remote sensing is very important. So here, for example, we have made an attempt here for prospecting bauxite deposits by spectrometric analysis of the Koraput district of Orissa. And you can see the different end members we have identified, like laterite, like bauxite, like your mud, like vegetation, like soil, red soil. So we have identified the end members, and based on these end members from the this satellite-based spectral data, then we have classified it. Okay, some advanced technique, and we can have these red areas are the possible areas of bauxite. Now, this one of these important areas in remote sensing and GIS techniques in geosciences is geological hazard assessment. So geological hazards may be many. So here one of the geological hazards, particularly in hilly areas, in the landslide hazard. So this is an example of the landslide hazard framework, how landslide hazard generation can be done. So here this we have used the satellite image, which is a pan and this multispectral data and panchromatic high resolution data merged product used for interpreting different kind of geological thematic information like geology, geomorphology, like this. And we have used the topographic information like digital elevation model, and together then we have interpreted this using the existing information as well, followed by field ground truths. And then after that, this we have a GIS database has been created from these thematic maps converted to the GIS database. So this structuring and organization of the database is important. Then this data integration Okay, there are many advanced techniques. It is a very simple technique, index overlay. You can have information value, you can have fuzzy logic, you have many kinds of weights of evidence, many kinds of techniques are available for integration. So finally, landslide hazard donation or risk assessment of the this area has been prepared. So this study was done for northeastern area from Shillong to Aizawl. So you can see this red means it is a very high hazard zones. So this is the area where landslide can occur frequently. But whereas this green or this blue, there is landslide. The chances of landslide is very less. Now this is one of the this application for geoenvironmental studies. So you can see this is a mining area. We have used multi-sensor approach. So here we have used the optical data, we have used thermal data, we have used radar remote sensing data, this microwave data. So all this information we have used together and different this geological this your indicators related to environmental impact assessment that we have identified and delineated. So here you can see in a mining area, this is the Jeria coalfield in Dhanbad. So what are these environmental indicators? Those have geological implications like subsurface fire, surface fire, subsurface fire, coal fire is very important in this coalfield for environmental study. So that we have identified from the thermal remote sensing data. Whereas there are the coal dumps, then there is the overburden dumps, okay, then closed mines, okay, those kind of information we have this identified from the radar remote sensing, particularly is a advanced technique, interferometric radar technique. Whereas there are certain very general kind of information like open cast query, this is and this coal washery and these water bodies, those can be very easily identified from the multispectral optical data. So we use multispectral optical data for this kind of information. We have used radar interferometric SAR data for this kind of information and thermal data for this fire related, thermal related information. So all those information together, all those multi-sensor data used together, we have this complete geoenvironmental map. But in this particular coal field, there is another problem is land subsidence as well. So for land subsidence, there is an advanced technique of interferometric SAR, differential interferometric SAR technique is involved. So using that technique, we can detect, we can delineate, and we can measure and model this land subsidence due to mining and land subsidence due to coal fire. Okay, so that I have a slide later on. So here, this is one of the applications is de-insert technique, differential interferometric SAR technique for land subsidence. So land subsidence can occur due to mining, due to groundwater overdraft or groundwater over extraction or groundwater pumping. Okay, so in case of Calcutta city, we have made a nice attempt, and this is the differential interprogram we have made, and based on some advanced processing, we have identified this area which is slowly subsiding, which was slowly subsiding, and the subsidence rate at the time of our observation was around 6 to 7 millimeter per year. So that very nicely we have identified, and that we have compared and validated with respect to groundwater level depletion scenario. Okay, so if you understand, if you identify the area which is groundwater depletion, which area is affected by severe groundwater depletion, then you can take the measures. So you can recharge groundwater so that the groundwater level can be improved. So this kind of study is very helpful for this preventive measures of major collapse. This is very important, and this work has been done with other collaborative agencies. Similarly, in case of mining area, this is also we can do this the detecting and mapping the subsiding areas. So this is in case of Jharia coalfield, you can see this is C-band differential interprogram, and this is L-band. C-band is 5.6 centimeter wavelength, and L-band is 23 centimeter wavelength. Okay, so we can identify the fringes very nicely. These fringes means these are the subsidence affected areas. So subsidence affected areas we have identified very nicely from C-band and L-band, and that you can see in the field also how this land is subsiding, and due to the subsidence, particular differential subsidence, you can see there is a these cracks, these white cracks are developed, and this subsidence what we have measured by the satellite based technique, that by C-band or L-band, that we have validated with respect to leveling, that is the ground based measurement technique. So these measurements are matching they are very close to each other. So that means whatever the measurements we can get it from the satellite data, by this technique is very much matching with the ground-based measurements. And here you can see the arrows. It says that in this particular direction, this ground is displacing horizontally. So this kind of information we can extract for different kind of geological this your phenomena like landslide, like an earthquake, and this land subsidence, as I've already explained to you. For glaciology also, that we can use in case of volcanic deformation also we can do. So these are the some of the advanced applications in in geosciences using remote sensing.